Yes, good morning, students. We were discussing about the digital transmission through Bandlimited. Sorry, additive weight Gaussian noise channels, right? I said here uh, we are modeling channel as a linear filter, okay, with a bandwidth limitation. Means we are restricting the bandwidth of the channel to certain frequency. Okay, so it can pass only certain range of frequencies, not all frequencies. What I mean to say is the bandwidth of the channel will be restricted to certain value. Okay, and I said another important thing is we can model channel as a linear filter. The moment I say filter, you all need to visualize and recall what are the different types of filters you have studied so far in a different semesters, right? Is it possible to say from your end what are the filters you have studied in the DSP? At least in the lab, I think you have done also. Yes, be fast, quickly. I would like to hear from your end.
Chebyshev filter, Butterworth filter.
Very good. Only those two filters, Chebyshev and Butterworth. Yes, anybody else to add on to this? So among these two, which one is low pass, which one is high pass? Or both are low pass, or both are high pass? Yes, other students I'm asking. I think Skanda has told about Chebyshev and Butterworth filters, right? Yes, you don't want to add any value to this? Yes, nobody can come forward, say, yes, we have studied so and so filters. You might have conducted experiment also, at least a simulation. Semester is also online, right? Okay. At least you might have simulated using MATLAB or whatever other tool you may be using it, and you have seen the frequency response of that filters, right? And you know how to vary the gain of that filter. So the moment I say filter means it will have pass band and as well as stop band, right? Okay, so nobody is ready to talk. Others don't want to add any value. What Skanda has told to that.
The Chebyshev is a low-pass filter.
Very good. Yeah. Yes, anybody else? What about other filter? What Butterworth filter? Yes, Butterworth filter. Yes, Naurin has added Chebyshev filter is a low pass filter. Like that, I think some more students are there, 27 as of now. See, out of 27, only 2 are communicating. What about others? I am asking the known facts. It is not that I am asking something new which you have not studied so far, right? Whatever you have studied, that one only I am asking you people to recall and say what are the filters you have studied, and even you have done practicals also, I said. Okay, fine. Let me continue with this. And I was telling and I was giving examples about the band limited channels, right? One is the telephone channel. As I said, basically the telephone channel is used for the transmission of voice, right? As I used to say, voice frequency is from 300 hertz to 3400 hertz. It will be rounded off to 4 kilohertz and it will be sampled at 8 kilohertz, right? And after digitization, it will be sent at 64 kbps, right? Similarly, the microwave line of sight radio channel is also a band limited channel. Then the satellite channels and underwater acoustic channels also. So whatever the channels you take, they're all limited in bandwidth. Okay? Just I gave with pictures what are the band limited channels. So the satellite channels, then microwave line of sight channels, okay, underwater acoustic channels. And then I was told about when you transmit a signal, right, through a band limited channel. So what happens? So that signal has to satisfy that bandwidth criteria, right, which is imposed by the channel. Otherwise, what happens? It leads to distortion. Okay, so as the signal is transmitted through the channel, it is getting distorted. Okay, so that distortion leads to intersymbol interference, I said, right? So what happens? Because of that intersymbol interference at the demodulator side, so there will be an increase in the probability of error at the detector side. So to nullify this intersymbol interference, so there are methods or devices known as channel equalizers. Okay, so they are one of the widely used methods for correcting the channel distortion. Fine. And I said what is the frequency response of the channel. So it looks like this. C of f in time domain, we say it is C of t, right? The band limited channel is characterized as a linear filter with impulse response C of t, and its frequency response is denoted as C of f. So which looks like this. This is the frequency response of the channel. How do we express this mathematically? So this is the Fourier transform of C of t. That is the definition, right? C of f is equal to integral from minus infinity to infinity C of t into e power minus j2 pi ft into dt, right? So looking at this frequency response of the channel, what we understand is it can pass only certain range of frequencies, right? So it is limited to the frequency W hertz, right? So it is if the channel is basically a baseband channel, which is limited to BC hertz, what we can say the C of f will be 0 when f is greater than BC hertz, right? So any frequency component with frequency higher than this FC hertz or BC hertz, what we say, will not be passed by the channel. So because it is band limited to W hertz. This is the frequency response, that is magnitude, and this one is the phase response of the channel. Okay, so we are not worried much about the phase response. We are interested in the magnitude response. Yeah. As I said, we model channel as a filter. So to understand that, we all know filter, we treat it as a LTA system, right? Linear time invariant system, having the impulse response of the channel here denoted as C of t, right? So if input is GT of t, if I say the input to the channel is a band limited to W hertz, and even the channel bandwidth is also limited to W hertz, then I represent the input signal to the channel as GT of t, right? And when I apply that as input to the LTA system, which I am making as a channel, right? So output of that LTA system will be what? Convolution of input and the impulse response of the channel, right? So we know how to write the convolution of two signals, right? C of t is the impulse response of the channel, and GT of t is the input signal, right? So convolution of those two signals will be the output of that channel, or we say LTA system, right? So in integral form, we can write, if I denote output of the channel as h of t, then I can write integral from minus infinity to infinity C of tau gt of t minus tau into d tau. So you all know the convolutional integral formula. So just I'm writing that, right? So in frequency domain, what I said, in frequency domain, what happens if two signals are convolved in time domain? It will be equal to the multiplication of their Fourier transform in the frequency domain. So that is what is written here. So h of f is equal to C of f into gt of f, right? So C of t is the Fourier transform C of f, and a capital GT of f is the Fourier transform of GT of t. So multiplication of their Fourier transform in the frequency domain. Okay. Yeah. So diagrammatically it is shown here. So, yes, so I said the channel will be modeled as a linear filter, right? I said its impulse response will be denoted as C of t. In frequency domain we can write it as C of f. Similarly, the input signal is also and this is limited to WHz, and the input signal is also limited to WHz, right? So in time domain I represent that input signal as GT of t, and its Fourier transform will be called GT of f. So output of the channel in time domain I represent it as H of t, so which is equal to what? C of t converted with GT of t. Accordingly, in frequency domain I can write H of f is equal to C of f into GT of f, right? So then this is the channel, okay? So this is the channel. We treat this channel as an what? Additive white Gaussian noise channel. So the noise is added into the channel, and I write that noise as N of t. I denote mathematically the noise as N of t. Then output of that will be what? Means the received signal will be what? R of t we say. Okay, R of t, which is equal to what? H of t plus N of t. Okay, so noise will be added to the output of the channel. Is this fine? So as I said, assume that the signal at the input of the demodulator, that is output of the channel, is corrupted by what? Additive white Gaussian noise. So the moment we say Gaussian noise, that is additive white Gaussian noise, you all should be able to visualize the Gaussian pulse. Okay, that is the bell curve. Yes, if it is non-Gaussian, then all these assumptions and derivations will be different. Okay, by assuming the noise is an additive white Gaussian, we are going to do all these derivations. Okay, so the signal is corrupted by additive white Gaussian noise, which is given as what I said. The received signal will be H of t plus N of t, where N of t is the additive white Gaussian noise. As I said, we model the channel as a linear filter having a frequency response, right, limited to certain frequency range. Already I have shown the frequency response of the channel. Okay, I think you should be able to remember this response. So this is what the frequency response of the channel. Okay. So in the presence of additive white Gaussian noise, so the demodulator having a filter, so which is matched to the signal H of t, that will be maximizing the SNR at the output. So this is the definition of matched filter. Okay, so in the presence of additive white Gaussian noise, I repeat once again, the demodulator having a filter, right? Even if you recall the matched filter receiver, right? What is the first block? First block is an LTA system, right? And what will be its impulse response? You know, the impulse response of the matched filter. Then you are sampling at t is equal to capital T. Then you will get the output, right? By taking the maximization of that. So that is what I am saying here. So demodulator having a filter which is matched to the input signal, matched to the signal H of t, will maximize the SNR at the output. Okay. So the linear filter model for a band limited channel means you have to write this diagram. Okay. Okay. So how do we take up this mathematically, right? So let me say about this. So I am denoting the received signal by a notation was what? R of t. R of t is my received signal. So which is equal to what? H of t plus N of t, right? And I am passing this through the matched filter, right? That has the frequency response of what? This one. This received signal I am means maybe So you may be getting the doubt. I was talking about the filter, right? So two types of filter. This is about the transmitting filter. Okay. Since still I have not shown the full complete diagram of this transmission of a signal through a band limited channel, right? So, and here I started about the received signal, and then I'm saying that that received signal will be passed through a master filter, right? That has a frequency response of this. Means now what you need to assume is, so this is the transmitted signal, right? Means I'm going to receive R of t as a received signal, so which is what? H of t plus N of t. That will be passed through a filter, another filter which is there at the receiver side. Okay, even that filter what I'm using at the receiver side is also a matched filter. Okay, and the frequency response of that filter is given like this, that is gr of f. Means this is the frequency response of the receiver filter, okay, to the receiver side, so which is equal to h conjugate of f into e power minus j 2 pi f t naught. Okay, where t naught is the time delay at which the filter output is sampled. Okay, so t naught is the time delay at which the filter output is sampled. Then the signal component at the output of the master filter at the sampling instant at t is equal to t naught is given as, means the output of the master filter, right? So we say ys of t naught, means it is t at t is equal to t naught, which is equal to integral from minus infinity h of f square into d of mod of that. So it is nothing but what? Energy of the signal. That is why it is denoted as e suffix h. Okay. So ys of t naught is the what? This is the signal component at the output of the master filter at the sampling time t is equal to t naught, right? So ys of t naught is equal to, we say, integral from minus infinity to infinity h of f, okay, mod of that square into d of. So we know how do we define the energy of the signal, right? So it is nothing but energy of the signal, so I can denote it as e suffix h, right? So that is what I'm saying here, which is the energy in the channel output waveform h of t, right? Then what is the noise component? I can say the noise component at the output of the master filter, the noise component at the output of the master filter has what? Since it is additive and Gaussian, I said, means it is having zero mean and a power spectral density of what? This one, n naught by 2. Right? That is why I write the noise component at the output of the master filter having zero mean, and the power spectral density I denote that as Sn of f, which is equal to n naught by 2 into h of f square. And then this the noise power at the output of the master filter is having a variance, right? So sigma square n, which is equal to n naught by 2, I said, right? So I find the variance as what sigma square n is equal to integral minus infinity Sn of f into d of. What is Sn of f? Sn of f, that is the power spectral density of the noise at the output of the master filter, right? So I'm just substituting that. I'm substituting what is the value of Sn of f. So which is equal to n naught by 2 integral. This I know what is this one, right? Integral from minus infinity to infinity h of f mod square into d of is nothing but eh. So that is why I can write n naught into eh by 2 as my variance. Okay. So this is the variance. Then I can calculate what is the SNR at the output of the matched filter. So SNR means what? Signal to noise ratio. So I know what is the signal power, and I found what is the noise power, right? So I can say what is SNR at the output of the matched filter. So S by N, here I could not write the suffix as O. You can write that as suffix as O. Okay. So this is the what? Signal to noise ratio at the output of the matched filter. So which is equal to what I say? Signal power. Okay. That is means it is energy, what I said, EH. So power means it will be square, right? So that is why it is written E square H. Okay, E square H. And noise power. So noise power is about variance. That is what is I got noise power as N naught into EH by 2. So that is why I substitute here N naught into EH by 2. Then 1 EH will get cancelled. So I can write the output SNR or SNR is the output of the master filter, which is equal to what I can write. This 2 will go up, right? So 2 EH by N naught. Okay, so this is the expression for the SNR, that is signal to noise ratio at the output of the master filter. Okay, so the filter impulse response is matched to the received signal component h of t. Okay, so instead of the transmitted signal. So I will come back to this. What is that? Okay, filter impulse response is matched to the received signal component h of t instead of the transmitted signal. So when we see the block diagram of entire transmitter and receiver, then we will be able to understand this point. Yeah. So to implement the matched filter at the receiver, okay, I'm talking about the receiver side. So h of t, we note, right, or equivalent, the channel impulse response C of D must be known to the receiver, right? So the receiver should know what is the impulse response of the channel. Then only we will be able to design a filter at the receiver side which can match to the impulse response of the transmitting filter, right? So the performance of the system is determined by the signal energy, right? Then to maximize the received SNR, what we need to ensure that the spectrum of the transmitted signal waveform is limited to the bandwidth of the channel. Then only I can assure that the SNR at the receiver side is maximum. So this is one numerical based on whatever I have discussed so far. So this is how I represent my signal pulse. Okay, so GT of t is equal to 1 by 2, 1 plus cos of 2 pi by capital T of t minus t by 2, which exists over the interval 0 to t, and which is what is shown here. This is a half sine wave pulse. Okay, hope we are able to see this. See, half sine pulse can be represented mathematically like this. So this is what's shown here in diagram. GT of t, G capital T of t. Yes, is it possible to see this diagram? G capital T suffix, okay, of t. This is my half sine wave. I can express that mathematically like this. Okay, if this is my signal and this is the frequency response of the channel, right? So what is the output of the channel? That is GT of f. So that is what is calculated here. It is an impulse function. I think if we will be able to understand this, just able to get what I'm saying. So you need to find what is the Fourier transform of the signal. Okay. So if you're good at Fourier transform, you will be able to express this as a sinc function. So it takes time. Means it is cannot be looking at this. You will not be able to write directly. Okay. That is why means since it is in time domain, no? So in frequency domain it is easier to solve. That is why the Fourier transform of the signal is taken. So the Fourier transform of the signal GT of t is like this. Just try this one at your leisure time, whether you will be able to get this expression or not. We'll see. Okay. Then the spectrum of this is given here, the magnitude spectrum of that. So we say h of f is equal to what? C of f into GT of f. We know it, right? So this is my C of f, which is band limited to W hertz, having a magnitude of 1. Okay, and the Fourier transform of GT of f is this. So if I multiply those two, I can say what is h of f in frequency domain, so which is equal to GT of f when f is less than W, and it will be 0 otherwise. Okay. So hope you take time to solve in your free time. Just check whether we'll be able to get the Fourier transform of the signal will be like this or not. Yeah. Further, what we are doing is we are finding the signal component at the output of the filter, right? That is EH. So we know what is GT of F, right? So we are finding the signal energy. So which is what? It exists over the interval minus W to W. That is why it is written minus W GT of F square into DF. So just GT of F is substituted here. And after simplification, we get like this. Then we are finding what is the variance. Okay. In that, so we found variance as N0 EH by 2. Then the output SNR. I was telling now in the previous example who is missing, you can have a note of that. So output SNR, that is SNR at the output of the master filter, will be what? Means after simplification. Okay. After simplification, we can say it will be 2EH by N0. Even here substituting the value of GT of F. Okay. So then what is EH you are going to get? It is not completed. I think you should be able to simplify by substituting the limits and say what is the value of EH. Okay, here it is written. We have told what is the maximum value is EH, that is energy of the signal. That is why straight away it is taken there. Okay, so just have a look about this the example. So try by yourself finding the Fourier transform. Okay, so just what I told at the beginning. So this is my input signal. Here I have taken it as a square pulse, right? It may be unipolar, bipolar, any of the line coding type I said. And since the channel bandwidth is limited, it can pass only a signal of certain frequency, right? But to transmit, you all know what is the Fourier transform of a square pulse. Is it possible to say, any one of you, what is the Fourier transform of a square pulse or rectangular pulse? Yes, my dear students. Fourier transform of a rectangular pulse. Hello? Yes, nobody is ready to talk. I think you are going. Is it not reachable? What looking at this diagram, is it not possible to say what is the shape of this? What is the signal is? It is in the form of what? Here it is written, no? You can't say what is it. It is a sync function, okay? It is one of the standard signal. So rectangular pulse in time domain, its Fourier transform will be a sync function in the frequency domain. Even vice versa also. Means if I have a sync function in the time domain, its Fourier transform will be a rectangular pulse. That is why there is a restriction on the bandwidth. Means if the signal is band limited in time domain, okay, if the signal is band limited in time domain, so it cannot be band limited in frequency domain. Because what? If I say rectangular pulse, which is band limited to certain frequency, right? Then if I take the Fourier transform of the rectangular pulse in frequency domain, it will be a sync function. So sync function, what? It will not be zero exactly at outside that frequency, right? So its tail will extend till infinity. So that is why we say the signal which is band limited in time, it cannot be band limited in frequency. And even vice versa is also true. Yeah, that is one thing. And as I said, when I transmit this rectangular pulse through this band limited channel, output may not be exactly square wave pulse. Okay, it may be like this, whatever I have shown here. So means its width is getting widened. Okay, as it passes through the channel, it is going to spread. Okay, means so when it is going to spread, it will be I said overlapping with the, means the present symbol duration will be overlapping with the previous symbol duration, like that. So there will be overlap of consecutive symbols that leads to distortion. That distortion is known as the intersymbol interference, I said. So let me discuss in detail about that. So it is all just to get an idea what is that. So I think hope you can, of course, you may not be straight away able to get the visualization of that. Let me take proper example, I think. Uh, yeah. Yeah, able to see this diagram? Here, see, I have given a rectangular pulse as the input, and I said is a filter, which is a low pass filter. So I get output of that will be like the sinc function. Okay. Yes, if I'm not getting any response from your end, I don't know whether my network is connected with you people or not. Hello, or everybody is busy with something else. See, nobody is responding. Hello. See, 40 students are there. Nobody is ready to talk. Means what you people are doing, man? Hello, am I connected?
Yes, sir.
So my voice is clear, or is there any network issue?
It's clear, sir.
Hello,
Clear, sir.
clear. Okay. So able to see this input is a rectangular pulse, right? What is the output of that? So as I used to say, a channel will be modeled as a filter. So here I am considering it as a low pass filter, right? So hope you are able to see here at the filter data. This is my input data, right? Actually, it should be rectangular pulse, right? And I'm getting like this as a sinc function, right? What is happening here? Able to see the overlap of the present symbol with the previous symbol. Means if I here only one pulse is shown, for this one pulse I'm getting like this, right? If I have a series of pulses, so I will be getting series of sinc functions, right? So here one is shown here with respect to one pulse, right? Similarly the next one, and similarly the next one, right? So I have what? So there will be an overlap, no? Is it? Are you able to find that overlap of the present symbol with the previous symbol?
Yes, sir.
Yeah. So this is known as the intersymbol interference. Okay. So the filtering effect of the band limited channel will cause spreading of the individual data symbols as it passes through. Okay. So for consecutive symbols, this spreading causes part of the symbol energy to overlap with the neighboring symbols. So that leads to, or that we say as intersymbol interference. Okay. So because the channel is band limited, no? So when we say it is a band limited, we say it does the filtering operation, right? So that leads to the spreading of the individual data symbols as it passes through it. So for consecutive symbols, what happens? That spreading causes part of the symbol energy to overlap with the neighboring symbols. That we call as a intersymbol interference. So that is what I discussed. I have something to say here. Uh, means what I'm saying here is this is what the frequency response of the low pass filter, right? If I'm ideal frequency response will be what? A rectangular pulse like this, right? This is the ideal frequency response of a low pass filter. But in reality, what happens? There will be a pass band and a stop band. So I will not be able to achieve such a strict or straight or sharp difference between the pass band and the stop band, right? To achieve this, I need to have very high order filter, right? So you all know as the order of the filter increases, the complexity of the circuit also increases. That is why you all know with first order what is the attenuation in the stop band for low pass filter. For the second order, what is the stop band in the what is the attenuation in the stop band? Is it possible to say for first order at what rate the gain falls for first order, and similarly for the second order? So hope you understand what you mean by order of the filter. Hello, order of the filter. You might have studied at least second order filters, no, in your some subject.
Yes, sir.
Yeah. Order of the filter. How do we define order of the filter? Based on what components? Say, let us consider low pass filter only. To say it is a first order filter, based on what components we say, okay, it is a first order or second order or third order? Yes, no idea? How do we determine the order of the filter? Yes, come on, students, please respond. Order of the filter. So based on the number of RC components in the filter, right? So if it is a first order, we say only one R and C component will be there. Okay, to say second order, we will have two RC components. Okay, so for first order, for low pass filter, we say the gain reduces at what rate? Minus 20 dB per decade increase in the frequency. Okay, so that is why after pass band, in the stop band, there will be attenuation of the signal. At what rate it will be decreased? It will be of what value? Minus 20 dB per decade increase in the frequency for the first order. Okay, for the second order, it will be minus 40 dB per decade increase in the frequency. So I hope I thought you were aware of this. Okay, so based on that, here it is shown. So it is of the frequency response of the low pass filter. Okay, so I think I will quickly take the other continuation of this. I think that is better. Yeah, actually I should say this and then I should discuss about other things. So hope you are able to see the block diagram of this digital PAM system. Yes, any one of you, is it possible to just read out the blocks? So this is a block diagram of digital PAM transmission through the band limited baseband channels. Yes, what is the first block?
Transmitting filter.
Yeah. So this digital PAM transmission, you should have this thing in mind. We are using two filters, one at the transmitter side and another one is at the receiver side. Okay, so that is why it is written transmitting filter and its frequency response as GT of F. Right. Similarly, to the receiver side, receiving filter having a frequency response of GR of F. Okay, first your input data, okay, which is in the form of zeros and ones, will be represented by any of the line code. That first will be passed through a transmitting filter. Okay, so which we call it as a pulse shaping filter. It is transmitting filter. Then the output of the transmitting filter is denoted as V of t. That will be applied as input to the channel. So we know what is the channel frequency response, right? Which is denoted as C of F. So you know what is C of F? So which is equal to integral from minus to infinity. What is the input to the channel? V of t, right? So V of tau, we can say, right, into C of t minus tau into d tau. Like that, you should be able to write the expression. Then noise will be added to the output of the channel, right, which is we call as additive with Gaussian noise. And then this output of the channel is it will be represented as h of t, then what is R of t? It will be h of t plus n of t, right? So that is given as input to the receiving filter, and we know what is the frequency response of the receiving filter. So which will be same as that of the transmitting filter, right? Then output of the receiving filter will be sampled. And that is why it is passed through a sampler, right? And at t is equal to t naught. Then it is given to the detector to estimate the transmitted symbols. Okay. So this is the block diagram of digital PAM system, I said. So transmitting filter, right? Then the linear channel with additive white Gaussian noise, then the receiving filter, then the sampler, I said. So that will be periodically samples the output of the receiving filter, then the detector, symbol detector. So these are the main blocks of the digital PAM transmission system. And here symbol timing estimator is there, right? Means it has to sample at t is equal to the symbol duration. T is equal to t naught, something I said, right? So that will be estimated by this one, symbol timing estimator. So the sampler needs the timing signal which is extracted from the received signal to serve as a clock to specify the appropriate time instance to sample the output of the receiving filter. Okay, from the received signal only, this circuit will be able to extract the clock. Okay, and it will be able to find out what is the duration of the received signal. So only it will be sampled at that duration. Okay. Yeah. So the input binary data sequence having a bit rate, we denote that by R suffix B from the source, right, is a subdivided into k bit symbols, and each symbol is mapped into the corresponding amplitude level, which will be modulating the output of the transmitting filter. That is why it is called PAM signal, pulse amplitude modulation. Pulse amplitude modulated signal, it is PAM signal means. Okay, means so amplitude of the pulse means here two things are there. One is your symbol data, another one will be the carrier. So depending upon the input symbol, the amplitude of the carrier will be varied. Okay, hope you will be able to visualize that PAM signal. I think that you have studied, I think I taught in the previous semester, I hope, if I am correct. PAM signal, pulse amplitude modulated signal. Okay, so amplitude of the pulse is varied. Okay, so the baseband signal at the output of the transmitting filter means I'm denoting that as V of t, right? So how do we denote that? So this A suffix n is the amplitude level. Okay, so this gt of t minus n into t is the what? Is the pulse. Okay, and here the value of n varies from minus infinity to infinity. Means I have infinite number of pulses, right? And each pulse having a value of that magnitude, that is a suffix n is written, right? Means when n is 0, the amplitude of the signal will be a naught, I can say. Okay, then when n is 1, the amplitude of this pulse will be a1 into gt of t. Gt of t minus t will get, right? So I hope you can extend, means it's a summation form, right? By substituting the value of n is 0, 1, 2, 3, like that you can write, so that even for n is equal to minus value also. So then you will be able to understand, okay, how the pulse of the signal is varied, means the amplitude of the pulse is varied, right? That is from minus infinity to plus infinity. So in a simple form, it is written with the summation equation. Hope you are able to get this equation, right? Vary the value of n from minus infinity to infinity. Just write that. So as I said, to begin with, substitute n is equal to 0. If I substitute n is equal to 0, what I can write? a naught into gt of t I can write, right? Because n is equal to 0. Then when n is equal to 1, so first term is what? When n is equal to 0, it is a naught gt of t. Then when n is 1, it is a1 gt of t minus t will get. Gt of t minus capital T, because n is 1. Then when n is 2, a2 into gt of t minus 2t. Right? So gt of t minus 1t, 2t, 3t, and so on is our shifted version of the signal which is there at the baseband, and which is multiplied by the amplitude of the signal. Okay, even the amplitude level will vary based on the magnitude. Okay, so this is output of the transmitting filter, and this will be given as input to the channel. Okay, so as I said, RB is the bit rate, and AN is the what sequence of amplitude levels corresponding to the sequence of k bit blocks of the information bits. Is able to visualize this signal? Take, say for example, 10 rectangular pulses only. Okay, so each rectangular pulse amplitude will be different. Okay, you think A0, A1, A2, A3. You take some numerical values. A0 is 1 volt, then A1 is 2 volts, A2 is 3 volts, like that. Then you are summing up all those things and writing it in a simplified form. Then R of T, right? In the same way, here, what is R of T? That is output of the channel, right? So I can write the received signal at the demodulator, or we say the channel output is what R of T is equal to summation n is equal to minus into infinity an h of t minus nt plus noise. Okay, so you know what is this h of t minus nt? That is the output of the channel, right? Which is nothing but what? H of t is c of t converted with input signal. Okay, so here this is h of t, output of the channel, right? So input is what? V of t, and channel impulse response is c of t. So convolution of those two will be the output of this, which we have discussed earlier, right? Yeah. So in the same way, even this is also written in the form of summation. Okay, h of t minus nt with the different amplitudes plus the noise. Okay, so h of t, as I said, is the impulse response of the cascade of the transmitting filter and the channel. So which is what? H of t is equal to c of t converted with gt of t, where c of t is the impulse response of the channel and n of t is the additive Gaussian noise, right? So this received signal will be passed through what? The receiving filter, right? So a linear receiving filter, and its impulse response is known as what? Gr of t, and its frequency response will be capital Gr of f. And even I said what is the, how do we express this Gr of f, right? And if in time domain, what we say, if the impulse response of the receiver filter is matched to the impulse response of the channel output, then its output will be, this output SNR will become maximum, right? And if you do the proper sampling at the instant. So what I can write, output of the receiving filter, which is denoted as y of t, right? So this y of t will be equal to what? Summation of n is equal to minus into infinity an into x of t minus nt plus w of t. So this x of t minus nt is what? Yeah. So this is again amplitude of the pulse, and this is the shifted version of the pulse, right? Plus the noise. Okay. Yeah. So where x of t will be equal to h of t is converted with the impulse response of the receiving filter. So what is h of t? It is the convolution of c of t into input signal, right? So gt of t converted to c of t is h of t, So which is converted with the impulse response of the receiving filter. So that is why here is written x of t is equal to gt of t converted with c of t, which is again converted with gr of t. Okay, so w of t is a noise I said, right? So n of t is converted with impulse response of the receiving filter gr of t. Since it is additive noise at the output of the receiving filter. Then to recover the information symbols. So this is my information symbol, right? AN. Output of the receiving filter is sampled periodically with the interval of t seconds. Hence, I can write output of the sampler. So, with respect to this block diagram, that is output of the sampler y of kt, right? So, which is equal to what? I can write output of the sampler will be y of m into t, which is equal to summation n is equal to minus into infinity an x of what I said in the previous case, it was t minus n suffix n into capital T, right? So here that t, capital T is nothing but small t. Small t is nothing but m into t, right? So that is why it is written y of mt. Wherever t is there, small t, replace that small t by m into capital T. So that is what done here. Here in x of mt minus nt plus w of mt, right? So I can write this as what? In a simplified way, I can just denote with a suffix y suffix m, means m symbol will be equal to an into x suffix m minus n plus w. Okay, so if I substitute the value of from n is equal to 0, that is from minus to infinity, then I can write when n is 0, so it will be what? X naught, right? X naught when this is for the case what I have taken first term when m is equal to n. So when m is equal to n, it becomes x naught, right? Right. So that is why it is written am into x naught. Then same thing when n is not equal to m, right? So this x suffix m can be written as what? It's an x of mt, and this w suffix m as what? W of m into capital T. So where the value of m can vary from 0 to, that is from 0 plus or minus 1 plus or minus 2 and so on. Okay, so this is how the simplified version of the output of the receiver. Yeah, I think let me stop with this.